Hello, this is Doris Ann Mertz. Welcome to ACT Math Prep Part 3, where we're going to go over some geometry, plane geometry, and maybe a little bit of coordinate geometry later. Anyways, let's get right into it. All right. You're going to need to have some of these formulas memorized for like the area of a circle, the circumference of a circle, the area of a rectangle, the perimeter of a rectangle. So let's just go over some of these. So the area of a circle is pi times the radius square. And the radius is this length. This length is the diameter. So that's just a little vocab review. And the circumference is equal to 2 pi r, or pi times the diameter, whichever way you want to think of it. So these you do have to memorize. Now the volume of a sphere, that one you probably will not have to memorize. That would be given in a note on the question, or at least it has in the ones I've seen. So the volume of a sphere is 4/3 of pi r cubed. So that one you don't have to memorize. Now let's talk about the volume of a cylinder. You can either memorize the formula, which is pi r square h, or you can just think about it, that the volume would be equal to the area of this circle times the height. So you're basically finding the area of the circle and multiplying it by the height. Now this is probably going to come into play in word problems where they're going to ask you something about filling up a cylinder. So that would be the volume of a cylinder. Now sometimes there'll be a word problem that talks about painting some kind of cylinder on the outside, and that would be a surface area question. And I don't memorize this formula. I just think about it. And you think about if you were going to paint it, you'd have to paint the top and the bottom, which is basically pi r square. That's the area times 2. So you'd have 2 pi r square. And then you'd have to paint this, which is going to be, the length of it is going to be the same as the circumference here. So the circumference would be 2 pi r. And then the height of it, that would be your width or your height. So it's going to be 2 pi r times your height. So you're going to have the two circles, so 2 pi r square plus 2 pi r times the height. So you don't have to memorize that formula, just think it through if they ask you about painting the outside of a cylinder. Okay, the area of a rectangle is just the length times the width, pretty easy, and the perimeter is just the length plus the width times 2. If it's square, you know, it's the side squared, and the perimeter is just 4 times each side. So the volume of a rectangular prism is the length times the width times the height. That's pretty easy. Now the surface area you have to think a little more about. So if you were asked to paint the outside of a rectangular prism of some kind, then you would have to paint the top and the bottom, the left and the right side, and the front and the back. So you got to do 2 times the length times the width. So that covered the top and the bottom. You got to do 2 times the length times the height, and that would cover the front and the back, and then 2 times the width times the height. That cover the 2 sides. The volume of a cube is just the sides cubed, and the surface area of a cube. You have six sides on a cube, so it'd be 6 s squared. All right, the volume of a cone, more than likely, you would probably be given that, but if you're not, it's pi r squared times 1/3 of the height. So it's 1/3 pi r squared h. Oh, I wanted to talk a little bit about the length of an arc. An arc would be like this is an arc out here. And so if you had an arc that was, say, 90 degrees, you had an arc that covered 1/4 of this circle, you would put 90 over, so whatever the degrees were inside of that angle, you'd put 90 over 360 and times it by the perimeter, because you're basically just taking a proportion of that perimeter for the length of the arc. Similarly, the area of a sector, that's the area inside of your little portion of the pie. So it would be this, or if you had marked it off at the 90 degrees, it'd be, you know, this whole quarter here, and it'd be like 90 degrees over 360, or 1/4 times the total area. So you just proportion it out based on the degree angle of that inside of the arc there. All right, Let's talk about parallelograms. The area of a parallelogram, you got to pay attention to this. It's the length times the height. Don't make the mistake that I have in the past of doing the length times the width. That's not how you do it. Usually you'll have to use your Pythagorean theorem or something and figure out the height. Sometimes it may be given to you, but it's the length times the height. The perimeter is similar to a rectangle. It's you add the length and the width and times it by 2 because you got 2 of each. If the length is equal to the width, that's called a rhombus, just in case you need to know that vocab. Let's talk about trapezoids. The area of a trapezoid, you're going to have to look at your two bases and you're going to have to average them. So it's going to be base 1 plus base 2 divided by 2. So you're getting your average of your bases times your height. So that's how you get the area of a trapezoid. Triangles, all triangles, the area of a triangle is half of the base times the height. So basically, if you had a rectangle and you put a diagonal through there, you'd break it into 2 triangles. So it's half the base times the height. All right, let's talk a little bit about some special kinds of triangles called right triangles. When you have a right triangle, you can find the length of the sides. If you have 2 of them, you can find the other one by using the Pythagorean theorem. So the Pythagorean theorem says that a squared plus b squared equals c squared. C is always your hypotenuse here. That's how we label it. But anyways, whichever 2 you are given, you can get the other one to stand alone to get the answer for that. So if it wanted to know b and you were given a and c, you would reconfigure the problem and then you'd end up with b equals the square root of a squared plus c squared. So, now there's some special triangles, some ideas we can use to help us save a lot of time. These are very important. Pay attention to this. This is the most important to remember is a 3, 4, 5 triangle. So this is a special right triangle. This only applies on right triangles, so they'll be identified with the little square in the corner. But so if they gave you one leg as being 3 and the hypotenuse as being 5, you'd know that the other side was 4. And it works for multiples of 3, 4, 5. So it could be a 6, 8, 10, or a 9, 12, 15, or a 300, 400, 500. So that's the most important one to remember. And that, I promise, will save you some time on the test. Similarly, we have a 5, 12, 13 triangle. That one shows up probably the second most of these special numbered ones. And then you don't see these as often, but every now and then you'll see one that's an 8, 15, 17, or a 7, 24, 25. But if you've got a limited memory or a limited amount of time, just remember the 3, 4, 5 and the 5, 12, 13 and their multiples. Also, try to remember these special triangles. This is an isosceles triangle or 45-degree triangle. These 2 sides are equal. They're both x. And when you have this kind of triangle, the hypotenuse is always x times the square root of 2. When you have a 30, 60, 90 triangle, the side opposite of the smallest angle will be your smallest side. That'll be x. The side opposite of your largest angle, which will be your 90-degree angle, will be 2x. And then the side opposite of your 60-degree angle will be x times the square root of 3. So these 2 are easy to remember, the x and the 2x. And this will be your only one that you might struggle a little remembering, but it's x times the square root of 3, and it's opposite of your 60-degree angle. These will help you save time. All right, let's do an example. A ramp for loading trucks is 13 feet long and covers 12 feet along the level ground as shown below. How many feet high is the highest point on the ramp? So we want to know how many feet high is this. Now, you could use the Pythagorean theorem if you don't remember our special right triangles, but you can save a lot of time if you remember the 5, 12, 13. This will take you like 15 seconds to do this one, and you can circle J because you know that this side is a 5. All right, members of the fire department lean a 30-foot ladder against a building. The side of the building is perpendicular to the level ground so that the base of the ladder is 10 feet away from the base of the building. To the nearest foot, how far up the building does the ladder reach? So we're going to have to draw a triangle, and we're going to use the Pythagorean theorem, and we're going to have to actually calculate, and it's wanting to know the nearest foot, so we're going to be rounding off. So let's draw it. We got a ladder, it's 30 feet long. We're putting it 10 feet from the wall. We want to know how high up the wall it reaches. So we do the a squared plus b squared equals c squared and put the 10 and 30 in there. 10 squared is 100, 30 squared is 900. We try to get a alone, so we get 900 minus 100 over there to get 800, and then we take the square root of that. So the square root of 800, you would put this into your calculator. The square root of 800 is 28.28, and the answer would be 28 for the nearest number. All right, a ladder is 10 feet long and reaches 8 feet up a wall as shown below. How many feet is the bottom of the ladder from the base of the wall? Once again, you could use your Pythagorean theorem to figure this, but if you remember the 3, 4, 5 and that multiples of 3, 4, 5, you could quickly look at this one and know the answer is 6. All right, in the figure below, a highway, this is kind of a long word problem, but it's not hard once you get down to it. A highway rest area at D and radar stations at A and B lie on a level east-west line. A is 9,000 feet due west of D. An airplane at C is shown directly above the rest area, flying due west at a constant speed of 300 feet per second and a constant altitude of 12,000 feet. The airplane is located at a straight line distance of 15,000 from the radar station at A and 13,000 from the radar station at B. So that's all just setting up the problem. Here's the actual question. Which of the following values is closest to the distance in feet between the two radar stations? So we're wanting to know the distance between A and B. We already know this distance between A and D. We just have to figure out this distance between D and B. And we know that we could figure that one with the Pythagorean theorem because we got this distance of 12,000 on one leg and the hypotenuse is 13,000. But if we remember our 5, 12, 13 triangle and multiples of that, we would quickly know that this is 5,000. And if they want to know A to B, it's just 5,000 plus 9,000 equals 14,000. Okay, a little bit about angles. Complementary angles are angles that add up to 90 degrees, and supplementary angles are angles that add up to 180, a straight line. If two parallel lines are cut by a transverse line, then 8 angles are formed, and your odd angles here are all going to be equal, and your even angles here will all be equal, congruent to each other, let's say, not equal. All right, interior angles of polygons. So it's really important to know, and I'm sure you all know that the triangle has 180 degrees on the inside of it, and a square or a rectangle has 360 degrees. But if you were asked to know the degrees of some of these other pentagons, hexagons, octagons, there's this neat little formula where you just do 180 degrees times n minus 2. If you forget that formula, you can remember that the number, the degrees in a triangle is 180. So you can kind of figure out that it's the n minus 2 part. But anyways, it's 180 degrees times n minus 2. So an octagon, it would be 180 degrees times n is 8 minus 2. That makes 6. So 180 times 6 is 1,080 degrees. All right, let's use our supplementary angles and triangle knowledge to solve this one. In the figure below, vertices D and F of triangle DEF lie on line CG. The measure of CDE, angle CDE is 148 degrees, and the measure of angle EFG is 140 degrees. What is the measure of DEF? Well, we know that these 3 angles are going to add up to 180 because they're in a triangle. We know that these 2 are going to add up to 180 because they're supplementary. So this one would be 32. We know these 2 add up to 180 because they're supplementary. So this would be 40. 32 and 40 make 72. And if you subtract that from 180, we're going to get 108. So J of 108. All right, in the figure below, A, D, C, and E are collinear. AD, BD, and BC are all the same length, so they're all congruent as indicated by this little line. And the angle measure of angle ABD is as marked, 25 degrees. What is the degree measure of angle BCE. This is the one we're wanting to know. And you can read that problem, but really everything they've told you in the problem, you can just see in the diagram. And the ACT is pretty good about drawing you very accurate diagrams. And you may just want to look at the end, the sentence at the end asking you the question. Or you can go ahead and read the whole description if you're more comfortable with that. But anyways, we got to find this angle. We're given 25 degrees here. So how do we get started? Well, we know that these two lengths are congruent. And if they're congruent, then those two angles are going to be congruent. So 25 degrees and 25 degrees. Those two add up to 50. So we know that this angle has to be 130 degrees. If this angle is 130 degrees, the supplementary angle here will be 50 degrees. Now these two are congruent. So if this one is 50 degrees, this one is 50 degrees. And if this one is 50 degrees, this one has to be 130 to be supplementary. So you can just figure that all out by looking at the graph. You can do it much more quickly than I'm describing it. I'm just trying to describe how you get to the answer there. All right, that's enough for the plane geometry, and I'll see you again. Thank you for watching ACT Math Part 3.